Hello, in this video we will explore how the idea of momentum can allow us to predict how objects move after collision with each other. We will investigate how momentum is changing when mass and velocity is changing. Consider a truck and a car moving with same velocity. The mass of the truck is 4 times the mass of the car. Hence, the momentum of the truck will be greater than the car. In the second situation, we keep the mass constant. We investigate the momentum of the same car traveling with different velocity and see how the momentum is affected by the change in velocity of the object. Here car B has a greater momentum compared with car A and car C, because it is moving with the greatest velocity. Car A has zero momentum. Car C has momentum but lesser than car B and greater than car A. Momentum depends on the velocities. Mass and velocity are combined to give a single quantity called the momentum. Momentum is the product of mass and velocity. We represent the momentum with a letter P. The unit of the momentum is kilogram meter per second. Momentum is a vector quantity and the direction of the momentum is the same as the direction of the object's velocity. We can see that collisions are happening all around us all the time. They happen on the microscopic scale of atoms and electrons and macroscopic scale in space. Let us consider the Springy collision. In case 1, let us see what happens when a moving object B collides head-on with a second object A, which is at rest. The moving object B stops and the object A initially at rest moves off with the same velocity as that of object B. To achieve this condition, the collision should be head-on and there should not be any spin on the moving object. In case 2, two identical objects moving with different velocities collide head-on. If the collision is springy, they both move backward and their velocity will be swapped. The object initially moving slowly bounces back faster and the object initially moving fast will bounce back with the speed of slow one. In another case, if the moving object B collides with an identical stationary object A, they both move off together after the collision. The speed of the combined object is the half that of the original moving object B. It is as if the motion of the original object has been shared between the two. When the mass of the trolley increased as a result of the sticky collision, its velocity decreased. Doubling the mass halves the velocity and so on. In the above collision, there is change in momentum and kinetic energy of the objects before and after the collision. Depending on the total change in momentum and change in kinetic energy of the objects before and after the collision in a closed system, we can differentiate the collisions as perfectly elastic collision and an inelastic collision. To identify the perfectly elastic collision, we take an example of two identical objects A and B moving with the same speed in the opposite direction have a head-on collision. Each object bounces back with its velocity reversed. We must now see how the momentum and kinetic energy changes before and after the collision. Object A with mass m and velocity positive v moving to the right which is the positive direction, will have a momentum mv, and the object B, which is moving in the opposite direction with mass m and velocity negative v, moving to the left, will have the momentum minus mv. So the total momentum before the collision is the sum of the momentum of the object A and object B, which is equal to mv plus minus mv, which will be 0. The total kinetic energy will be the sum of the kinetic energy of A and B, which is half mv square plus half mv square equals to mv square. After the collision, the object bounces back, so the velocity is reversed. The total momentum after the collision of the object will also be 0. The total kinetic energy after the collision is mv square. In this example, the total momentum before and after the collision is 0. The kinetic energy before and after the collision is mv square. Both momentum and kinetic energy before and after the collision are unchanged in a system where there is no external force acts on them, which is referred to as closed system. In this collision, the object have a relative speed of 2v before the collision. After the collision, the velocities are reversed, so the relative speed is 2v again. In a perfectly elastic collision, the relative speed of approach is equal to the relative speed of separation. This is a feature of perfectly elastic collision. Consider the inelastic collision. The same two objects collide and stick together and come to a halt after moving a small distance. The momentum before the collision is the sum of the momentum of object A and object B. The object A is not moving, so the momentum is 0. And for B, the momentum is minus mv. So the total momentum is minus mv. The total kinetic energy before the collision is the sum of the kinetic energy of individual objects. Kinetic energy of object A is 0. Kinetic energy of the object B is half mv square. So the total kinetic energy is half mv square. After the collision, two objects stick together, so the mass becomes double, and the velocity of the combined object will be half of the initial velocity. The momentum of the object is minus mv. The kinetic energy of the combined object will be 1 by 4 mv square for the small distance before it comes to halt. If the objects come to halt immediately after the collision, then kinetic energy is 0. In this situation, the momentum before and after the collision is minus mv and is conserved, but the kinetic energy before and after the collision is not same. After the collision, there is a decrease in kinetic energy. Kinetic energy is not conserved. The energy is lost because of the work done in deforming the two objects. There will be a change in the internal energy of the object. They get warmer or transferred as sound if the collision is noisy. In both the examples, we see that the momentum remains same before and after the collision. That is, momentum is always conserved in the collision. there is nothing else into which momentum can be converted. So we can state the conservation of momentum. For a closed system in any direction, total momentum of objects before collision is equal to the total momentum of the objects after collision. To summarize our discussion and to use this concept to solve the numerical problems related with elastic and inelastic collision, we can use the following equations. For elastic collision, in terms of momentum, m1u1 plus m2u2 before collision is equals to m1v1 plus m2v2 after the collision. For kinetic energy, half m1u1 square plus half m2u2 square equals to half m1v1 square plus half m2v2 square before and after the collisions. In terms of inelastic collision, we can use the momentum m1u1 plus m2u2 equals to m1 plus m2 times v. For kinetic energy, half m1u1 square plus half m2u2 square equals to half m1 plus m2 times v square. And to summarize how momentum, kinetic energy and total energy will be conserved, you can use the chart. For perfectly elastic collision, momentum and kinetic energy, total energy is conserved for the closed system. For inelastic collision, momentum and total energy is conserved, but kinetic energy is not conserved in the closed system. Thank you for watching the video.